Hello. So now we'll do the Venturi meter one more time, but this time it is designed for the gases. So since we discussed earlier, like the Venturi meter for the liquids, I cannot use the gases in place of liquid there because there was the opening there. So we have to close it. If you provide an opening in case of gas, there will be a lot of troubles there. So in case of gases, it's closed system we use. And in case of gases, it is more important to measure the velocity because with the velocity there comes the friction. With friction there can be a fire if there is a little bit air available there for the fire. So it's very important there. So let's discuss this structure first. So in this structure there is this one pipe and there is this another pipe and very variable cross-section areas. So this here it is A1 cross-section area, here it is A2 cross-section area, velocity V1, velocity V2, density of the gas is rho g, and these two pipes are connected by a uniform cross-section U-shaped pipe, and this pipe there is a liquid in the pipe. Generally that liquid is mercury. So there is a liquid, this pipe is filled up with the liquid. So when the flow will be happening, the surface of the liquid will have the uneven height. So there will be some delta H available there. So this delta H we measure, and we already know the value of rho g and rho L for liquid. There is a point, this point I am defining the pressure as PA, and this point I am defining the pressure at PB. So throughout this liquid, let's discuss now. We have to calculate V1 and V2 in terms of these things. So you see the pressure here I am defining as PB, and it will be same pressure here also. Meaning PB is nothing but P2. Similarly, when I say PA is nothing but PA, because you see between these 2 points there is only gas, and when it comes to the gas, density of gas is very small. So that rho g H component will almost be 0. Rho stands for density. So during that fall, we can assume the pressure remains same. Similarly, during that fall, we can assume the pressure remains same since it is a gas, but we cannot do for the liquid. So you see, this liquid is same throughout. So if this liquid is same throughout, the pressure here and the pressure at the same level here will be same. So at this point, the pressure will be same as P2 is equals to PB. So let's apply the fluid statistics first, pressure relationship first. So at this point pressure is PB or P2, and at this point pressure is P1, and between these 2 points there is a liquid rho L of density, and this delta H is there. So I can say P2 is equals to P1 plus rho L G delta H. This is my equation 1. At any point of time I can utilize this relationship. Now let's go up. So between these 2 pipes we have to apply. So first let's apply the continuity theorem, just like Venturi meter, previous case of Venturi meter. We'll apply the continuity theorem between 1 and 2. Theorem between 1 and 2. These are the points, not the equations. So point 1 and point 2. Point 1 and point 2. So it will be A1 V1 is equals to A2 V2. This is my equation 2. So area of cross section multiplied with velocity at point 1 and the area of cross section multiplied with velocity at point 2 is equal. Now let's apply the Bernoulli's equation between 1 and 2. We have one equation, we have 2 equations, and we have to go for third one. So Bernoulli's theorem between point 1 and point 2 will apply. Since this is a horizontal pipe, so we don't have to consider the gravitational potential energy component there. So it will be half rho V1 square plus P1 is equals to half rho V2 square plus P2. Now this P2 is equals to P1 plus rho Lg delta H. So we can replace the value of P2 from the equation 1. So from equation 1, if we put the value from equation 1, it will be half rho V1 square plus P1 is equals to half rho V2 square plus P1 plus rho Lg delta H. And you see, when I am taking rho here, it's for the gas, rho g. It is for the gas. It is for the gas, and this is also for the gas, and this is for the liquid. So you see this P1 and P1 is getting cancelled out. So this equation will be V1 square is equals to V2 square. So what we are doing, we are multiplying this whole equation by 2. So this half and half goes and 2 will go there. And we will divide this whole equation by rho g. So it will be V1 square is equals to V2 square plus here it will be 2 rho L upon rho g delta H. So this is my equation 3. This is my equation 3. Now we have equation 2 and equation 3 and we are having two variables V1 and V2. So let's replace the value of V2 from equation 2 into equation 3. So from equation 2 and 3 we put the value, so it becomes V1 square is equals to A1 square upon A2 square into V1 square plus 2 times of rho L upon rho g delta H. We'll take V1 on the left hand side. So it will be V1 square 1 minus A1 square upon A2 square is equals to 2 rho L upon rho g delta H. So we'll take this value here and we'll take the under root. So V1 will be equals to under root 2 rho L upon rho g delta H divided by 1 minus A1 square upon A2 square. That is the value of V1. Now, if you put this value of V1 into equation 2, you will get the, so from equation 2, so the value of V2 will come out to be A1 upon A2 under root 2 rho L upon rho g delta H divided by 1 minus A1 square upon A2 square. This is the value of V2 we are getting. So in this case, if you see, if I equate the rho L and rho g, same, meaning if in place of rho g, I am having the rho L only, we'll get the previous equation. Meaning if we are having only the liquid here, we'll have the previous equation, all the relationship will be valid for the Venturi meter for the liquid will be same. So here, since we are taking two types of things, meaning one is the gas and second is the rho L, this liquid, so we are getting this extra term. This term we are getting extra in these equations. So now you understand Venturi meter when we apply it for the gases, little bit modifications are happening and equations are same. The same way we are using the equations. So that's how we use this Bernoulli's theorem into the equation. So this is one of the application of Bernoulli's theorem. So I think you understood this concept. No. Thank you.